We're going to discuss two examples of how to calculate the electric and D field, so the E field and the D field, for a plane of dielectric material under two very different circumstances. So we're going to consider a semi-infinite plane. It'll be the same geometry in both cases. Actually, I don't know why I've called it semi-infinite. It's infinite in x and y and finite in z. So let me actually just remove the word semi. Infinite plane in x and in y. It's going to be a dielectric material, and we're going to think about two very different examples. In the first case, it's going to be a linear dielectric with an external field. It's not a very good x. Let me just... Okay, external field. In other words, we're applying a field to that system. And in the second case, it's going to be a nonlinear dielectric where there's a permanent polarization. It's going to be the same geometry for both cases. So let me just sketch that briefly. So we'll have a plane which goes off to infinity in these directions. And if you wanted to, you could consider it looking like this as well. This is going to be the z direction. Now, it's just important to remember that, and this will be true in both cases, if we have a plane of charge, an infinite plane of charge, then the electric field can be written as E is equal to sigma over 2 epsilon naught, where sigma is the charge density. Obviously, the sign of E changes depending on which side of the plane you are, but it doesn't depend on the distance away from the plane. So that's the first thing just to note. And then if we have two planes of opposite charge, and I hope you can see where this is going because we're going to be thinking about polarization charges, then the field is non-zero only between the two planes. And if you want to think about why that might be, then let me sketch the following. If I do the electric field due to the positive charge, it's going to be the upper plane, then it's going to look like this. But then let me actually also put it down here. For the negative plane, which is the lower plane, but let me put a minus there, it's going to look like this in the various different places. And if you were to sketch the total, then you'd see that you would get 0 at the top and 0 at the bottom because the two fields are in opposite directions, and in between we would have effectively a double. This is something that's going to be useful as we think about this example. So let's consider the first point, which is a linear dielectric. And we're assuming that we have an external field, E0. So how do we solve for the D field and the E field? Well, because we've got a dielectric, we want to use the field D. And so we can write that div D, the divergence of D, must equal 0. That's because there's no external charge density. We know that far away from the dielectric, D must equal epsilon naught multiplied by E0. So E0 is the applied field, so that's going to be uniform and it's going to be throughout space. Far away, D must equal epsilon naught E0, and we're writing something like E0 is equal to magnitude of E0 in the z direction. And D equals epsilon naught E0, where E0 is uniform, fulfills div D equals naught. So we can actually, therefore, we can deduce that actually D is equal to epsilon naught E0 everywhere. We can now deduce E. So E, therefore, inside, so E is obviously going to equal E naught away from the dielectric. Inside the dielectric, we can write that E is going to equal D divided by epsilon naught epsilon r. We can write that because this is a linear dielectric, and that's therefore going to equal E0 divided by epsilon r. We could, if we wanted to, deduce the polarization P, which we write as epsilon naught chi E times E, and notice that this is E and not E0, and that is therefore equal to epsilon naught epsilon r minus 1 divided by epsilon r times E0. And this is the really key point, is that the polarization in the material is linearly related to the total electric field in the material. That's why we use D, is because we couldn't actually do a self-consistent calculation of P and E in the material, but D allows us to find that. And we could, if we wanted to, also deduce the surface polarization charge density, and from that show that the electric field can be calculated. This is, of course, actually a circular argument. So that's a very simple example, but it does at least illustrate why D is useful. I'm sure that you could argue that we know that the electric field is reduced by a factor of epsilon r inside a linear dielectric, but that can be geometry dependent, and also we only know it because we have done this kind of calculation using D. Let's turn to a slightly more complex situation, certainly physically, and think about a material which is nonlinear with a frozen-in permanent polarization, a dielectric with P is equal to P in the Z direction. There are materials that do this, for instance barium titanate or lead titanate, though they're perhaps less common. Again, in this situation, we could once again say simply that the divergence of D must equal 0. Now, we're not given any specific boundary conditions in this case, but we can assume that D should be equal to 0 everywhere, simply because geometrically, if there's no charge at all to create D, and we know that our system has the geometry of an infinite plane in X and Y, then the fields must be directed along Z, and we can argue that E itself would be 0 far away from the plane because we know that it's a neutral dielectric, and therefore this is a reasonable assumption for the D field. Having assumed that, we can deduce that E must therefore equal minus P divided by epsilon naught inside the dielectric. And so we notice that this is clearly a non-linear dielectric because E and P are no longer related in the simple way with chi E that we had discussed before. The other way to do this actually is to consider the polarization charges. So rho P must equal 0 because the divergence of P is equal to 0 because P is uniform. Sigma P is going to have two values. It's going to be plus P on the top of the slab, and it's going to be minus P on the bottom of the slab. We know, therefore, that E is going to equal 0 outside the slab, for the reasons I outlined at the beginning. And inside the slab, we can write the following. We know that E is going to equal minus sigma over 2 epsilon naught, that's the field coming from the top sheet of charge, minus sigma over 2 epsilon naught, that's the field coming from the bottom charge, the negative one, in the Z direction, and that is just equal to minus P divided by epsilon naught. So we get the same result in two different ways. They are consistent as you would expect. If we now just consider a small piece of material which is polarized, so the electrical equivalent of a bar magnet, we'll just put some charges on here. We'll put a plus charge at the top and a minus charge at the bottom. Then we can think about what the different fields would look like. So the polarization is going to look like this. It's going to be uniform, and the polarization points from the minus sign to the plus sign. The D and the E fields outside will have exactly the same shape, and they will look like the field of a dipole when you go far away. So the field lines at the top will point away, the field lines at the bottom will come near, and then outside we're going to have this kind of typical dipole-like shape. But what's going to happen inside the dielectric? dielectric? That's the key question. And here we have to appeal to the boundary conditions. We know that the normal components of D are continuous across a boundary where there's no external charge. And so here, these lines of field must be continuous. They must form closed loops, just like this. Now, E, however, is going to start and finish on polarization charges. So when we consider the shape of the field lines of E, then we have the same shape outside, give or take a factor of epsilon naught in terms of magnitude. But inside, the E field will actually be pointing in the opposite direction. And I've put together a Jupyter notebook of this particular system. It's just worth thinking about the effects of nonlinearity. So there we have two simple examples, one linear, one nonlinear. In both cases, we used D to calculate the fields. It's generally easiest when you're dealing with dielectrics, and this plane geometry makes it very simple.